Good afternoon and welcome back to the calculus class. So in our previous class we discussed about the basic terminology of the derivatives. Today we will discuss about some application of derivatives. So first of all we will do this problem to find tangent line to a given curve at any given point. So our given curve is x to 5x cubed minus 3x squared plus 4 and the given point is x equals to 1. Mentioned that it is given only the x coordinate of the point and we have to find the y coordinates from here. So before doing any further calculation we need to know the formula for tangent line to a given curve. The formula is y minus y1 equals to m x minus x1. Here x1 is given, x1 equals to 1 and y1 is the y value at point 1. So to find this y1 we need to plug in y1 here, y value x value here, so it is a 5 times 1 cubed minus 3 times 1 squared plus 4, which is 5 minus 3 plus 4, that is 6. Okay. So now we got our point x1 equals to 1, y1 equals to 6. So this is our coordinates. So the coordinates, the point is on 6. Now let's find the slope. So slope m equals to dy dx at the given point x equals to 1. Let's find the derivative. So the derivative is dy dx equals to the first derivative of the given curve, 5x cubed minus 3x squared plus 4. We all know the formula to finding the first derivative. So 5 times 3x squared minus 3 times 2x plus 0. The derivative of the constant is 0. So we get 15x squared minus 6x. Now m equals to dy dx at point 1, so is 15 times 1 squared minus 6 times 1, which is 15 minus 6, that is 9. So our value of the slope at point 1 is 9. Now implement this formula. So we get y minus the one value is 6, slope m equals to 9, x minus x coordinate of the point is 1. Now simplify 9x minus 9, so that y equals to 9x minus 9 plus 6, so y equals to 9x minus 3. So that is our tangent line to the given curve. Now let's do some optimization problem. Before going to optimization problem, we can review the problem here. So our basic terminologies are here, the slope and the coordinates of the given point. So here x coordinate is 1, y coordinate is 6. We can find it by plugging in the given curve, and we need to find the slope m at point x equals to 1. So how do we find the slope? We need to find the first derivative of y and then plugging in x value, and we get the slope m equals to 9. Okay, so now let's do some optimization problem. So the optimization problem is find all local maxima and minima of fx equals to x cubed minus 6x squared plus 9x plus 3. Here it is a cubic function. So to find the local maxima and local minima, we have to find the first derivative, which is f dash x. So the f dash x is 3x squared minus 12x plus 9, and the second derivative is 6x minus 12. Now, to find the local maxima or local minima, we have to use on condition. At local maximum, local minima, the first derivative has to be 0. So the first derivative has to be 0, means this is 0. Now simplify this and solve for x. We have 3 times x squared minus 4x plus 3 equals to 0. Dividing by 3 from both sides, we get 4x plus 3 equals to 0. Now, so to find the x coordinates, we can simplify this as minus 3x minus x plus 3. How do we do that? So you know about the factorization problem from algebra. So we can factorize it. So we can expand the middle term minus 4x as minus 3x and minus x, so that if we multiply minus 3x and x, we get 3x squared, and also if we multiply the two ends, I mean x squared and 3, we get 3x squared. So we have common x from the first two terms, x minus 3, and if we take common negative 1, we have x, and here is 3, 0. Okay, so now see, here x minus 3 is a factor, and here it is x minus 3 is a factor. So x minus 3, if I take x minus 3 from both terms, so I have x here and minus 1 here, which is 0. Now solving this, we get x equals to either 3 or x equals to 1. So we have 2 points for x equals to 1 and x equals to 3. So I don't know who is on is a maximum, who is on is minimum. These are the critical points, critical numbers. So to find, to determine whether which critical number is maximum and which critical number is minima, we need to check the second derivative. So the second derivative here, if the second derivative is positive for any critical number, then the critical number is a minima, and if the second derivative is negative for a critical number, then the critical number is a maximum. Now plug in x equals to 3 first. So we have a second derivative at 3, 6 times 3 minus 12, which is 6 times 3 is 18 minus 12, which is 6. That is positive. That's why a function at 3 is a local minima. f3 is a local minima. Now for x equals to 1, a second derivative of 1 equals to 6 times 1 minus 12, which is negative 6, that is less than 0. So f of 1 is a local maxima. So we can find the local minima and local maxima, I mean exact value. So what are the exact values? So the exact values are here. So f3, what is f3? So plug in f3. So f3 is 3 cubed minus 6 times 3 squared plus 9 times 3, uh, 9 times 3 and plus 3, which is 27 minus 54 plus 27 plus 3, which is 3. So 3 comma 3, this point is a local minima. Again, f1 is 1 cubed minus 6 times 1 squared plus 9 times 1 plus 3, which is 1 minus 6 plus 9 plus 3, that is 7. So 1 comma 7 is the point, is a local maxima. That's it. So how to find local minimum, local maxima? So first of all, we need to find the first derivative and equate it with 0. Solve for x. So after solving, we get x equals to 1 and x equals to 3. So to find which point is the local minimum, which point is the local maxima, we need to do the second derivative test. So at point 3, the second derivative is 6, which is positive, so that f3 is a local minima. And at point 1, the second derivative is negative, so that x equals to 1, f1 is a local maxima. And to find the exact value of local minima, local maxima, so just plug in the values and we'll get the result. Now let's do another problem. We're using the derivative, find the okay. So the problem is, of all the rectangles with a perimeter of 56 feet, find the dimension of the one with the largest area. So this is another problem of optimization. So here given a rectangle, so let's draw a rectangle here, and let us consider the length is x and width is y. So this side is x, this side is y. So what is the perimeter? Perimeter P, let's say the perimeter is P. P is x plus y plus x plus y, which is 2x plus 2y. And given that the perimeter is 56, so 2x plus 2y equals to 56. Now solve for y. We get, dividing by 2, we get x plus y equals to 56 over 2, which is 28. So that y equals to 28 minus x. Now let's use the area formula. The area A equals to length times width, so x times y, which is x times 28 minus x, that is 28x minus x squared. So this is the value of area. Now we need to maximize the area, I mean the largest area. We need to find the dimension of the rectangle which provide the largest area. So find the derivative of a dA over dx. The derivative is 28 minus 2x, and for the largest area the first derivative has to be 0. Now solve for x. 2x equals to 28 and x equals to 14. Okay, what is the second derivative? So the second derivative is d squared a over dx squared, which is ddx of 28 minus 2x, which is minus 2. Now look at the derivative, the second derivative. The second derivative is negative 2. Since the second derivative is negative 2, we can see that the critical number x equals to 14 provides d squared a over dx squared equals to negative 2, which is less than 0. So the critical number, our critical number x equals to 14 is a maximum. Yeah. So x equals to 14 provides the maximum area of the rectangle. So the dimensions are length equals to 14 and the width y equals to 28 minus x. Where is the 28 minus x? Look at here. We have y equals to 28 minus x. So y equals to, use this formula, 28 minus x, which is 28 minus 14. That is 14. So the dimensions are 14 by 14. Thank you very much.